Hi, hello, welcome everybody. I am ready for a new video and I have to apologize that I was not able in the past 3 months to upload anything new. I was very busy with making a lot of PowerPoint slides and doing a lot of presentation and traveling. So there was no time to generate a YouTube video as my main job, of course, took me most of the time. But today I got something really fancy for you. So this is discussion on Touchstone file and cascading and connecting Touchstone file and extracting impedance from the Touchstone file, which originates from some discussion I had with a customer. Actually, it's a friend more than a customer. Hello, Patrick. This is the explanation for what we have seen. And the good thing is actually when you look in my YouTube channel, the highest click rate is the video about RLC values from S parameters, how to calculate RLC values from S parameter over Z parameters. If you didn't watch it, I highly recommend to watch it first before going into this one, because this one will be a deep dive. So how it started is actually that we had a measurement file, a measured touchstone file of our inductor. I don't have the measurements here. I don't do measurements. I do simulation, but basically the setup itself is you can generate the same amount or so the same type of data as from a measurement, of course, with a simulation. So we have an inductor, which is mounted over a ground plane of a PCB, okay? That's something like 200 microns, so like one thickness of a PCB layer. And I connected this a little bit strange. You will see in a minute why I connected it this way. But basically, you could imagine SMA connector here, SMA connector here, and you measure a two-port touchstone file. And then we take this touchstone file. Sorry, that's not the one. We go here. Then we take the touchstone file, and like I'm explaining in the other video, we calculate the impedance. I will not extract inductances today. I will just stick with impedances, but the path is explained in the other video. So what I do here is short the second port. Basically, we create a loop, right? We drive port 1, port 2 is shorted, we create a loop, and we measure the impedance of the loop. And what we get is of this inductor, it's what you would expect from an inductor. It's a high frequency behavior of the inductor, so at the low frequency, it's inductive, and then you have a so-called self-resonant frequency. At this frequency, there is a resonance, and then the inductor stops being an inductor and behaves like a capacitor. So far, so good. That's what you expect from a high-frequency model of an inductor. And when we have this, we can of course take this and match it to an RLC model, right? So this is the high frequency parasitic model of our inductor, which here we have 13 microhenry and a parallel capacitance of 3.6 picofarad. So I match these values to make sure that now the impedance of the inductor here, as you would measure it, or which is contained in the touchstone file, matches with the impedance of my RLC model. And if we look here at the Z parameters, you see them match perfectly. Of course, I spent a little bit of time of tweaking the values, but it's not really complicated to get these models. If you know what are the nominal values, you just add this parasitic capacitance, and here you go. You have an RLC model, which gives you exactly the same impedance as the touchstone file. So far, so good. Everything looking great. Where's the problem? The problem started when we wanted to cascade these models. That's where the problem started. So the idea was to take the measurement of one inductor and say we cascade these two inductors to obtain like the loop impedance of both inductor in series. That's what you would expect. Unfortunately, it somehow didn't work, because if we look at the Z parameters, so 1 is the cascading of the touchstone file, 2 is the cascading of the equivalent models. And if we now look at this, they look very different. So even if the impedance previously looked correct of the standalone inductor, the impedance of the both inductors cascaded after one after the other in terms of series cascading, they do not match at all. You see, the one with the touchstone file has me like 2 peaks, and the one with the equivalent model that I have extracted is only 1 peak. What's happening here? And that's a very interesting case, and that's what I would like to discuss with you. And the first and the most important thing is, of course, the measurement you are doing here. It's not only measuring, of course, the inductor, it's also measuring the traces, right? I didn't do any de-embedding here in this case. It's the raw touchstone from here to there. And now, of course, if you look at this, it should become obvious that the signal traces connecting to the inductor on both hands, they also have a certain capacitance to ground. And that means that this capacitance is contained in the touchstone file, but this capacitance is not contained in the RLC model they have generated here. And that's the difference between. So which one is the correct one? Of course, we can check it. We can now build a 3D model of both inductor in series, right? We don't need to cascade the touchstone files. We can put this two. We can put this two inductors in the 3D model. I separated them to have, let's say, to reduce the coupling between the inductors. I don't want to include it because if you cascade the touchstone files, you also do not include any of the couplings, right? So that's what I did, and now you understand why I had this strange trace form in the original model, because now I just mirrored the one inductor to the other side, and now we have only two ports. And we go the same way, right? I now drive port 1 and short port 2. Basically, I generate this whole series loop. And if we look for the setup of the full 3D model into the impedance, we see it is really containing these two peaks, right? Of course, we have now, what do we have? We have a capacitive section, the inductor, second capacitive section, inductor, another capacitive section. And we can confirm this if we now if we go back here and we take the cascaded, so that's not the RLC model cascaded, it's the cascading of the touchstone file, and compare the cascading of the touchstone file to the 3D model where we have both inductors, you see they match pretty well. So that means that the cascading of the touchstone file is the right approach. I mean, as you would expect, right? People using touchstone file for many years, and even sometimes there are people who doubt the simulation. Dealing with touchstone is standard theory from 1950s, right? So we don't do anything wrong, and every circuit simulator you will find which supports touchstone will give you exactly the same results. The point is that we actually did generate a wrong RLC model, because what we have, if we consider that we have this capacitances to ground, we need to include this capacitances to ground in the RLC model. So what I did now, instead of doing this this parallel capacitance of the inductor, and now notice, I called it by purpose in the beginning, I called it the self-resonant frequency of the inductor, but this is not correct. I mean, it is if you see this curve, right? If you see the Z11 here, you would immediately say, ah, yeah, that's the self-resonant frequency, but it's not the self-resonant frequency, it's the self-resonant frequency of the whole measurement setup and not only of the inductor. So I can build a much better model by taking now, so we had 3.6 pico in parallel, and if we take 2 times 3.6 pico in series, basically, right? That's how the current can flow. It's the exactly same thing. So I take the 3.6 picofarad and put them at the beginning, like thinking this is the capacitance of the trace 1 and trace 2. And now if we compare, of course, the standalone touchstone file of the one inductor and the equivalent circuit I built, it also matches perfectly. The thing is here, right? I mean, from maybe graduate school, somehow, as a young university student, you probably learned that there is always the possibility to convert a series to a parallel circuit. And that's exactly what I'm doing here. So this circuit, the second circuit, also has the same impedance as the touchstone file, right? And now if we continue, and now we cascade it, like I did before, if we cascade this particular model where we have the shunt capacitances, now that's the 3 is the cascading of the touchstone file, 4 is the cascading of my shunt capacitance model. And if we look at them, they match very well, right? So now I have selected the proper I have selected the proper RLC model to mimic the behavior of the touchstone file. Now the question you might ask yourself, if I do it this way, if I match in this way, with the parallel resistance, can I get rid of the effect of the ground plane, right? If you think about this, the cascading of this particular model, when we have the a series resistance, it gives me only one peak. It behaves somehow like the wood. It behaves somehow like there is no capacitance. However, we can test this by building a 3D model which is without the ground, right? I can also do a one-port setup, removing the ground and measuring basically the Z11 between the two ends of this signal traces. Let's call it signal traces without the ground. And of course, this one does not match the case where I cascade the two RLC circuit with the series capacitance. It's just by coincidence that for this particular standalone model, and not, I mean, for the standalone model, it's just you made this one match, but it still does not mean that you got rid of the capacitance to ground, because if you get rid of the capacitance to ground, like I did in the 3D model now, right, you get a different response than cascading this model. So simply saying at this point, this equivalent circuit I have chosen for my inductor is just not the right one. It just matches the impedance, and you don't see the, I mean, on a standalone, just one inductor, you don't see the difference, but it's still not the right circuit. And now we can do a few more fancy things. What I did in this discussion, actually, we can do the following. We can cascade this to Touchstone files like I did. So this is what we had previously seen, but you can do this cascading and the generation of the loop through the Touchstone file also in a different way. Now it's becoming a little bit strange, but you can do a Touchstone also like this. So what you define in this way is you're trying to force basically the current through the inductors, right? And you say, I do not allow any current to flow to ground. So I have a closed loop over here, but no current to ground because I put the high ohmic resistor there. Will this be the same? I mean, this is of course something different in terms of the Touchstone file like this one, but it's also not really neutralizing this capacitances to ground, right? So if we look at this, so Z11 is the one with two peaks, and Z22 is the one with the with one peak, right? So I don't have this ground currents. What's happening? Again, it's kind of, we have to understand this. Well, we can understand this much better by looking again at the equivalent circuits. So basically, if you do a setup like this, where you say I don't allow a current flow to ground. Basically, this is your resulting circuit. You're taking, so we saw this is the one inductor, this is the second inductor now with the shunt setup. And by defining it this way, basically, I'm defining a circuit like this, okay? So if you see Z22 and Z33 are now very similar, right? So this is the transformation I'm doing basically by defining a circuit like this. And that's maybe not what you would expect. So manipulating this Touchstone file on a circuit can be quite, let's say, quite challenging, and you have to understand what you're doing. The funny thing in this case now, in this case, when I do a definition like this, when I don't allow any current, when I have the shunt capacitances, but I don't allow the shunt capacitance to flow to ground, right? I don't allow the capacitance to flow basically into this loop, right? Because in a standard setup like this, basically you have also a ground here, and the current can flow through this capacitances to this position. In this setup, it cannot. So you have basically shorted all of your capacitances, but they are not connected to ground. They are not allowed to make the current flow over to the loop, to these inductors. And now, the crazy thing is that this actually results in the same setup like my my series capacitance setup. So Z33 and Z44 are the same, and they are the same like what I have cheated here by doing this strange setup. However, this works because of one reason. This works because the capacitance to ground is dominating. So what I said, like the self-capacitance of the inductor, it's not the self-capacitance of the inductor. We see mainly the capacitance of the traces to ground. Because if we make a following change, it's the same setup. I'm having the same inductor here, right? Okay. And what I did is I increased the self-capacitance of the inductor. Now the self-capacitance, how I do it? I take this model, so this is a ferrite model, and I simply increase the value of the permittivity. So in the original model, the permittivity here has a value of 3. Now I increase it to 30, which means I am increasing the self-capacitance, but I keep the capacitance of the signal traces the same, right? That's what I'm doing. And now if we start matching, you see now this self-capacitance, so I have the calculation of the standalone inductor, and if I define a circuit like this, again, I can make this Z parameters match each other in a standalone inductor by using 6.2 picofarad. Previously it was 3.6. So you see, I have to increase this parallel capacitance to make this match. So I have increased the self-capacitance. And if I now continue, however, and I build the same approach like I did in the previous case, I get rid of this parallel capacitance and I use capacitances to ground for the shunt capacitances and compare them to the cascaded model. So this cascaded model with the higher self-resonant frequency. So Z11, it's the impedance of the cascaded model, and Z22 is now the model with the shunt capacitances, again taking basically the value of we have seen here 6.2 and putting 6.2 into the shunt capacitances, and you can see that the agreement becomes worse, right? Previously these two curves with these two peaks, they were lying perfectly on each other. Now the agreement becomes worse, and that simply the reason is because the previous model was completely dominated by the capacitance of the traces towards ground, and the self-capacitance of the inductor just didn't play a role at all. But now, as I have increased the self-capacitances of the inductor, this simple model is not valid. So what do we need? Obviously, we need a model with the series and the shunt capacitances. And that's exactly what I did here. And I know that these values, like the sum of this capacitance has to be the same, right? So what I do is I select a series cap, and then I take the shunt values from the simple model and subtract the series cap from it. So the series cap is now 1.5 picofarad, and the shunt cap is 4.7, which is the value here, which we had 6.2 minus 1.5 to have the overall capacitance keeping fixed, but now distributed the overall capacitances among the capacitance to shunt, among the shunt and among the series capacitances, right? And if we now compare, so this is the Z11 of the Touchstone again, this is the one with just the shunt capacitances, and the Z33 is now the one when I have a mixed capacitance. I have now both the series and the shunt capacitances match each other, and you see this model now agrees much, much better. Of course, because this is now a much more complete description of the setup. So this is the problem. In the first case, it was just sufficient to keep the shunt capacitances simply because the series capacitance of the inductor was too small, was small enough that we could neglect it. But to get the full picture, you actually need also the full model, including shunt and series capacitance. And then you can see that again, the Touchstone files, they won't let you down. The Touchstone file and the measurement, they the Touchstone file do the right thing. It's S-Parameters. It's a very good, stable theory, and I'm a big fan of this theory. However, it tells you one thing. If you obtain a measured file, you have to ask always yourself, although I'm saying this in the other video, what's contained inside this file, right? What are the effects? And the main point here was you receive this file telling you that this is the measurement of an inductor. But inside this Touchstone file, there's a lot of capacitances to ground, which comes from the signal trace and not from the inductors. And then this can lead to something a little bit confusing in the end. But putting it into one sentence, S-parameters are great, they work, but sometimes you need a little bit more time to understand what they do on the circuit, and that's exactly what I try to show here. Don't get confused by this transformation thing here. Maybe if you didn't understand this, the most important thing is if your equivalent models are correct and contain everything which is in the Touchstone file, both will work. And sometimes it's just not able to see it, like we had in this example. You are not able to see this mistake just by looking at the Z11 of one component. They were the same simply because you can do this transformation of series to parallel capacitance. So be careful what you're doing with the Touchstone file, but do trust them that they are handled right on the circuit. So far so good. Thank you very much for your attention. I hope you have enjoyed, and let's see when I can deliver the next video. I hope it won't be as long as the last time. So in this case, don't forget to subscribe and hit the like button. See you next time. Bye bye.